As I was saying, I'm Kerry Lynn, Vice President. I'll be running the meeting tonight in lieu of Paul, our President, who's joining us from India by Zoom. This is the 986th monthly meeting of ATMoB. We have a pretty full schedule tonight. So we have the annual board election as well as a lot of annual reports. So I'm just going to state up front that the annual reports will be made available to members, but we're just going to have the committee chairs summarize the report so that we can try to keep on schedule and get our speaker home to bed at a good hour. Next one, the observing annual report.
Glenn, are you with us tonight? Are you with us?
I'm here. Can you hear me?
We can.
Okay.
Do you want the mic? Sure, I'll hold on. So, I'm glad you got rid of the quote. We had a quote up here that was very anecdotal about Einstein's wife, and I didn't like it, and I have to do a little more research. We'll use that next month instead.
Rich, the usual protocol is to have the mic somewhere near your mouth.
Well, I know, but you know.
That's where the noise is coming from.
It's where the noise is coming from. So, there aren't many planets to look at in the evening sky, are there? Jupiter is all but gone in the glare of the sunset. Mars is at 1.8 astronomical units away, 5.2 arc seconds in diameter, a lowly magnitude 1.4, not very exciting. And Mercury will be on Superior conjunction, was at Superior conjunction on May 29th with the greatest elongation east on the 4th of July, and it'll stand 14 degrees above the western horizon. So that's a little bit of an opportunity to see Mercury if you haven't checked that out in a while. The rest of the planets are sort of in the morning sky. Venus is rising, like right after 2:30, 3 o'clock in the morning. You can see it in the east, very bright. You should consider trying daytime observations, either naked eye or telescopic observations. Greatest elongation was on May 31st, 43 degrees away from the sun. Saturn is rising around 1:30 in the morning. The rings are only tilted 3.4 degrees, which makes the planet's overall magnitude pretty low at 1.1. Rising higher every year and coming up out of the south, so that's a good sign. Neptune rises with Saturn. As a matter of fact, they're probably within the same 5-degree field of the finder scope. They're pretty close to each other in the sky. Wait, there was one more. Go back. Oh, that's it. Okay, so go to the next slide. So I was gonna highlight this modest lunar highlight of the month, but I figured he'd throw things at me if I did that. So so we won't do that. But I wanted to point out a lovely trio of craters that will be visible June 30th and July 1st. They are Theophilus, Cyrillus, and Katharina. They're really very pretty impact craters. Theophilus is on the top, Cyrillus is in the middle, Katharina is down below. This is Fracastorius right here. This is Mare Nectaris. And so in about a 4-day-old moon, those craters are on the terminator, and they're really cool to look at. They're about 60 miles across, easy to see, and they're just chock full of detail. So while we've got, Canadian wildfire smoke over us and the deep sky is all but gone, you might as well turn to the moon and double stars and the planets. Anyway, so that's the highlight of the month.
Never.
Now, Mario, you'll come around someday. I know you will. The double star of the month is Ras Algethii, is Alpha Hercules, STF 2140. This pair is magnitude 3.4 and 5.4, 4.6 arc seconds. An orange and a yellowish kind of star, 360 light years away. And there it is on that chart. It's an easy star to find. It's very pretty double star. Glenn, you want to chime in on the double star?
Say that again?
Do you want to chime in on this double star?
You said it all. It's a beautiful pair, especially with all the wildfire smoke we're getting. Give the double stars a good shot. This is a beauty.
Yeah, turn to double stars, you guys. All right, next slide. The variable star of the month is not T Corona Borealis, although it should be not forgotten. I decided to pick on our Corona Borealis. I think Glenn mentioned it last month, but it's a weird little variable star, isn't it now? It normally hovers around magnitude, 6. Every now and again, it drops down sometimes as low as magnitude 14. It's a sooty little star with lots of carbon soot in its atmosphere, and I think that contributes. I got to do more research on it. I just clicked this, I thought about it, and I didn't realize it was so cool. I mean, that's a really cool Leica. That's a 5-year Leica. So it's up at 6 magnitude most of the time, and then all of a sudden, whoosh, down it goes, and then slowly comes
Yeah,
back.
Rich, I can throw in a
Go.
few things. I've been looking at this star for a lot of times. I've been in the AVSO for 40 years, and this is one of the stars I've seen for a long time. I did check it out very briefly last night, despite the smoke that's in the sky. But right now, it's about what it usually is. It's around 6 magnitude, and it's a great star because I usually check it out about every third night. And as long as it's around 6 magnitude, wait for 3 nights and go again. And I just remember one year I was looking at it, it seemed to be just a little fainter. There are 2 stars. One is 5.6 magnitude, the other is 6.4, and that's usually in between them. And one time I know it seemed to be a little closer to the 6.4 magnitude stars. So I went out the next night and it seemed to be even a little bit fainter, but I really couldn't be sure. But I started looking at it every single night and it did start to go into a dive. This star can be at 6 magnitude for years. And then suddenly drops. It seems to be clouds of soot, some type of dust in the atmosphere of the star that blanks it out. So it's kind of a reverse nova. And again, it's fascinating. I usually a chart from the AVSO, a binocular chart, and when it starts to go below 8th magnitude, I'll get deeper charts from the AVSO. But again, it'll go from 6 magnitude all the way down to 14, even 15 sometimes. It can stay down there for years. It's very unpredictable. But I would say give it a shot and start looking for it the next clear night, which might be September or October. But hopefully we'll get some clear stars.
Perfect, thank you. The June challenge, we're just gonna scoot through these. I didn't include a lot of slides because I didn't want this part to drag the meeting down. And a lot of these things, I've been thinking about this long and hard the last few weeks with all this Canadian wildfire smoke, where these deep sky objects just melt into the bright sky. And they're almost impossible to view. And I'm really, Glenn and I are thinking about reevaluating these observers' challenges of the month to make them actually a little bit easier and a little bit more in line with what we all can do here.
11 p.m. it's well situated.
Wait, say again?
11 p.m. it'll be well situated.
Oh, I'm not saying it isn't well situated. I just think the sky is so bright with light pollution and the smoke doesn't help us out.
Well,
Some of these things just melt away. Oh, it's not that you can't find the location. It's that visual observers probably can't actually see the objects. But anyway, this galaxy trio in Draco is where the arrow shows it is. Next slide, please. There's a preliminary image by Doug Paul. Doug, we're just going to skip over this for now. I'm gonna have a roundup at in the July meeting. We'll cover all this good stuff then. Next slide is the July object. It's NGC 6181, a galaxy in Hercules. And while you're looking at the double star of the month, you might as well scoot up a little bit and see if you can pick this up. Kepler and Sander gives it 3 stars. And the bonus is, if you can't find this galaxy, scoot just a little further up and to the north and find NGC 6210, the Turtle Nebula. It's a really pretty planetary nebula. Easy to find, bright, easy to find. So check that out if you can't find the galaxy. All right, next slide. And that's a preliminary image of 6181 that Doug sent us. All right, next slide. So here's the clubhouse schedule for the Friday, Saturday, all through the summer. We'll be closed, well, most of the members are up at Stellafane, who would open the clubhouse, but you never know who's going to be up at the clubhouse. If you think there might be somebody up there and you're around on July 25th and 26th, call the clubhouse and see if anybody answers the phone. All right, next slide. Glenn and I are going to try an introduction to the summer night sky on Friday, August 15th, with a rain date of Saturday, August 16th. We were pretty unsuccessful with the events in the spring and in the winter and the spring, but hopefully we'll get some clear nights these nights and look at the summer sky. More about that in July. And so here's the outreach report, very short and sweet. Glenn and I presented the observing report at each of the club's monthly meetings. We also organized and ran an introduction to the autumn skies. Similar events were planned for the winter and spring were canceled due to inclement weather. Clubhouse was scheduled to be open on the Friday and Saturday weekends during the dark of the moon.
Our speaker tonight is Dr. Diana Hannikainen, and she'll be speaking about microquasars, black holes, and superfast jets. She's editor-in-chief at Sky and Telescope magazine. Microquasars are small-scale analogs of distant quasars. Instead of a supermassive black hole accreting matter from its host galaxy, microquasars consist of a stellar mass black hole accreting matter from a companion star. Both systems, though, shoot plasma jets at really high velocities into their surroundings. Dr. Hannikainen will review the main characteristics of microquasars, and show how studying them yields clues to the physics driving distant quasars. Dr. Hannikainen is editor-in-chief at Sky Telescope magazine. She studied for her Bachelor of Science in Physics and Astronomy at the University of Edinburgh in Scotland, then moved to Finland, in part to explore her Finnish roots. While there, she embarked on graduate studies at the University of Helsinki and received a master's followed by a PhD in astrophysics, the latter in conjunction with the University of Sydney in Australia. The subject of her PhD thesis was multiwavelength observations in X-ray and radio of microquasars, a topic she focused on throughout her time in research. In 2017, she switched careers and moved to Cambridge, Mass. to take up the position of observing editor and now editor-in-chief at Sky and Telescope. Please welcome Dr. Diana Hannikainen.
Okay, good evening, everybody. Sorry about that. I was not privy to the instructions of how to connect, but I'm absolutely delighted to be here tonight. It's so fun to talk to friendly faces. I often give talks to, audiences where I don't know anybody. In fact, it's actually a little bit harder to give a talk to friendly faces because I end up giggling a lot. But thank you all for being here this evening. I do want to share. I think my abstract was a little bit ambitious. I just want to share with you some of the fun things that I learned along the way about microquasars when I was studying them for my PhD thesis, and then later on when I was in research. So I think I'd like to start with opening my bottle of water so that it's ready for me. Just noting that black holes are probably something that most people are interested in at some point in their lives. Of course, as observers and as scientists, there are lots of things that grip our attention and things that we want to get interested in, but black holes are pretty cool. And we know that they lurk in the cores of galaxies, and we know that they're the ultimate endpoints of massive stars. And we also know that they're extremely compact objects from which not even light can escape. And so one of the questions that we pose as researchers, as scientists, is how can we observe? We can't really see black holes, of course, but what we can do is infer their behaviors, their properties, from what we can observe in their immediate environments. And there are several ways to do that. And one of them is something we've been doing for quite some time, and that is observing quasars. I suppose most of you are familiar with quasars. The first one to be identified as such in 1963 was 3C273 here in Virgo, and it was identified to be a really distant object at about 2.5 billion light years, and it puzzled astronomers at the time because it had this incredibly high output of energy, and the fact that it was at such a vast distance caused a lot of brow furrowing and a lot of scratching of heads. For those of you who don't know, I'm sure you're all familiar with it, but the word quasar comes from quasi-stellar radio source. It's just a contraction from the first couple of words there. Then so that was 1963. Then in the early to mid-70s, astronomers, especially in the UK, started mapping the sky, mapping parts of the sky with big arrays. And there was one such array which was the Cambridge 5-kilometer telescope. And with that, a bunch of astronomers, a research group led by Turlin, they pointed the telescope at 3C219. C stands for the Cambridge catalog, third Cambridge catalog, and these are all radio sources, and they pointed this telescope at 3C219, and they noticed, they noted in their research paper that the striking feature of the new map is the presence of a central radio component, which is the nucleus of the galaxy, and a jet pointing along the axis of the source. So this is the first time that we have an actual observation of a jet from a distant object, from a quasar that is mapped in the radio. And today, we know that there are about 1 million quasars. This is from a catalog from the from the Hillsark archive, and they list more than 1 million quasars. And quasars are all have a common morphology. You have the host galaxy, you have a supermassive black hole at the center of the host galaxy, so the core of the object, and two bipolar jets that shoot out at relativistic velocities in opposite directions. They encounter the intergalactic medium and they form these lobes where the sort of end of the jet hits the intergalactic medium. And they come in all shapes and sizes. Sometimes you only see one of the jets depending on the orientation of the source. Sometimes you see beautiful bipolar jets like you do here in Cygnus A. Sometimes you see all kinds of squiggly jets, but there are about 1 million out there that astronomers can study, point their telescopes at, and try and figure out what's going on around, you know, the central supermassive black hole and the shooting of the jets and so on. And what we know about quasars so far is that we know that their jets can extend for hundreds of thousands to possibly even millions of light years. The jets are ejected at really fast velocities. The term that's bandied about a lot is apparent superluminal motion. Of course, nothing can go faster than the speed of light, and that is why we use the word apparent, in fact. And this is a trick of geometry, and I have a little diagram that I will share with you afterwards. So we know that quasars are at very large distances, and we know that these jets are powered by supermassive black holes. We still don't know the exact mechanism by which jets are ejected. We don't know exactly what happens in the environments just around the black hole. And that is where we want to go to eventually. And we will get there by looking at possibly some other categories of sources. And here we have in the late 1970s, so the first jet from a quasar was 1975, that was a paper from 75. In 1979, so just 4 years later, Ralph Spencer, who was at Jodrell Bank at the time, he pointed his radio telescope at a target called SS433. We know it's in the galaxy, it's associated with a supernova remnant, and this is the first time that somebody noted that there was an angular size, so this is an extended radio source associated with SS433 that was observed at these radio wavelengths. So this is the first time that we note a jet-like, reference to a jet-like feature in a galactic source, so a source within our own Milky Way. At about the same time, Andy Fabian and Martin Rees, who is currently the Astronomer Royal for the UK, they were also looking at SS433. And they noted in their abstract, in their paper that appeared in Monthly Notices, that they think that, so this source exhibited these incredibly curious, like emission lines that appeared to move in the spectrum depending on when the observations were taken. And they speculated that these lines might originate in cooled blobs as accelerated in a double jet. So they're actually using the word jet now associated with this galactic object. And they said that further observations of this object may clarify the formation of the double and triple structures seen in quasars. So double and triple structures meaning the nucleus of the core, the host galaxy of the quasar, and the jets on either side. And so here they're already speculating in 1979 that maybe this galactic source that is exhibiting radio jets might prove helpful to understanding these distant quasars. And so not much happened during the 1980s. So at the end of the 70s, we have these observations of SS433. And people are just, sort of looking at things, pointing their radio telescopes here and there. And but in 1992, a very curious cover appeared on Nature published a rather curious cover with the title "A Microquasar at the Galactic Center." And there we see for the first time officially the word microquasar. It had been used sporadically in the 70s and 80s, but for a completely different source, and it never caught on, and it didn't really have anything to do with quasars or anything like that. So this is the first time in 1992 that we see the appearance of the word microquasar. And this is the work of Felix Mirabel and Juan Luis Rodriguez. And they pointed the telescope to the galactic center, to the center of the Milky Way. And there's this source called, with this telephone number here, 1E74, etc. It's also called the Great Annihilator. It was called the Great Annihilator because some earlier observations in the hard X-rays had fleeting signals maybe of electron-positron annihilation. And so that made them dub this source the Great Annihilator. But they pointed radio telescopes at this source, and they discovered these jets, these symmetrically ejected jets from this source. And so that was 1992, and they dubbed it microquasar, of course, because you can see the similarity. Here on the left we have the Great Annihilator, and here on the right we have 3C175. And so you can see they're morphologically very similar. You have the central source. Of course, here you don't see it, but it's mainly the extent of the jets in the bipolar directions. The only difference being that quasar jets extend, as I've already said, for hundreds of thousands to millions of light years, whereas, of course, the microquasar that's at the center of our galaxy, its jet extent would only be, 5 to 6, a handful of light years. So the next step in this tale of the microquasar is a couple of years later, the same bunch of people, Felix and Juan Luis, they detected apparent superluminal motion in the galaxy for the first time. And this was a source called GRS 1915 plus 105. All of these names, these nomenclatures, come from the various high-energy satellites that were operating at the time. When you have a specific satellite that discovers a source, you put a sort of abbreviation of the satellite at the start. And so GRS 1915 plus 105 was discovered by Granat Sigma, which was a Russian high-energy mission, and 1915 is the right ascension of the source, and plus 10 is the declination. Does anybody know what constellation that's in?
Hold on a second.
Hmm?
1915.
Isn't it Aquila?
Yes, yes, yes. Big stars over here. You get gold stars. So it's not, and so that's how a lot of these X-ray sources are designated. You get the abbreviation of the satellite followed by some combination of the right ascension and declination. And so, as I said before, superluminal motion, of course, you can't have superluminal motion, but it's just a trick of geometry. When you have the observer here and you have something moving at a very fast relativistic speeds, I mean, about 90% the speed of light or something, you have a very small angle between the observer and the direction of motion, and then it can appear as if this blob is moving at faster than the speed of light. It just gets everybody very excited, but it's just a trick of geometry. But so what is it that unites these two types of objects? Okay, I've already covered some things, but here we have again that beautiful radio image of Cygnus A. So Cygnus A there on the left. And if we zoom in to the nucleus there, the center of the galaxy, we have a supermassive black hole that is accreting matter from its host galaxy. It's accreting matter that swirls into an accretion disk around the supermassive black hole, and you have this ejection of jets of plasma in two directions, in both directions. And we observe the jets in the radio. In quasars, the accretion disk radiates at the optical ultraviolet wavelengths, and of course we can see the host galaxy with regular telescopes and so on. And with microquasars instead, the morphology is, as I said, very similar. We have a compact object. For the most part, the sources that I studied was black holes, but you can also have a neutron star, but we'll call it a compact object, black hole here. A black hole that's accreting matter from a Roche-filling companion star. So what happens, this is what's called an X-ray binary. Are you all familiar with X-ray binaries? Mostly, yeah. So when you look up in the sky and you look at the star, most stars that you see are in binary or multiple systems, and sometimes when you have two stars in a system and one is more massive than the other, it evolves faster than its companion. It goes through the final stages of evolution, explodes as a supernova, leaves behind a compact object. If the system survives that supernova explosion, then you have a compact object and its companion star that are still in orbit around each other. Then what happens is that the companion star starts to evolve and it starts to fill its Roche lobe, and at that point matter from the companion star starts to swirl towards the compact object and starts to build up this accretion disk around the compact object. And that accretion disk heats up through friction. It's just like, you know, if you take your hands and you rub them real fast together, they warm up. It's the same, well, similar process in all the layers of matter that are swirling around in that accretion disk around the black hole. And so in these X-ray binaries, where you have a compact object and a Roche lobe filling companion with the accretion disk, we've also observed these jet ejections. So we have a system that's very similar in terms of, let's say, processes as in quasars. So the question would be, currently we know of a couple dozen, maybe a few more. I've not really looked into the latest discoveries in microquasars, but there's a couple dozen, you know, maybe enough to fill one page of table in a book. So if we only have a couple dozen or so microquasars, but we have 1 million or more quasars, why would we spend time, resources, energy, etc., observing the microquasars when there are so few and they might be maybe not always observable and so on, whereas the whole sky is filled with quasars that we can point our telescopes to at any time if we wanted to probe the behavior of black holes. And the main reason is timescales. So phenomena as it occurs in the vicinity of a black hole is directly proportional to the mass of the black hole. So if you have, in quasars, you have supermassive black holes of the order of millions to possibly even 1 billion solar masses. In microquasars, those are stellar mass black holes, so they're of the order 10 solar masses approximately. So the smaller the black hole, the faster you can witness, the faster you see, the faster phenomena happen around the black hole. So things that take decades or millennia in quasars take only a few minutes in microquasars for us to observe. So as my student, one of my former students, Kari Kolinen, said, these are timescales. When you're observing microquasars, stellar mass black holes, they are timescales that are well adapted to the human astronomer. You don't have to wait thousands of years for something to occur. And he dubbed it astrophysics for the impatient, and I thought that was absolutely brilliant. And so here is a visual of the timescale. So this is 3C273, and actually that's not a very long time over which these events happen. We have the central source, and we see going down from the top left down and then back up there and all the way down, we see the evolution of a jet ejection event. As you can see from the top, the source is still quite compact. As we go down this is every few months, we start to see the evolution of this jet ejection event until finally, up at the top we're in 1998 and down at the bottom we're 2001, so that's a span of about 3 years. But it took about 3 years for us to observe the evolution of this particular jet ejection event. But look what happens when we look at GRS 1915 plus 105. Here we have that source I touched on earlier, and we have 5 observations, and it's essentially the same thing. That's the source when it's still compact, when there is no signature of a jet, and slowly we start to see this ejection event occur, and that's over the course of 1 month. So in 1 month we can follow quite closely as this event happens. Yes?
Is that meant to show, is there actually a reaction occurring with the core
of the microquasar? In other words, it looks like the core is shifting to the left in that picture. Is there an action and reaction, is my question?
The core is the plus here.
Correct.
And I think it's just the orientation of
Okay.
how the ejection is happening. So this is probably coming a little bit towards us, that's going away.
So the ejection is like low mass compared to the core itself.
Okay, that's a good question. What we might actually be seeing here, that's not matter itself, and that's shocks. So we're seeing the shock of the matter as it goes through but they did, in fact, when these observations were done in '95, they actually did think, they called those blobs, in fact, and they thought that they were actual matter, and they tried to measure them in terms of, how many half moon masses or whatever it was. But later, about 5 to 10 years later, they started understanding it was more the shocks as the matter, as the jet propagated through the interstellar medium, and as it's encountering different densities in the interstellar medium.
Question, does it look like the brightness is, a lot brighter at the top, and then as the jet event occurs, or is that an adjustment of the picture of the relative brightness? Like, is the red like the brightest at the top?
Yes, and that is because that's when the event is starting,
Okay.
and it's evolving, and then here it's dissipating already because it's going farther and farther from the central source.
Okay. So the central source itself is that dot in the middle.
It's the X in the middle, yeah.
Okay, got it.
That's sort of the central that we're not seeing here because it's not radiating in the radio.
That's what I get for sitting in the back.
It's not a very big X there, yeah. So, to move on to probing a little bit more as to what is going on physically in these sources, we have again the same picture I showed before. And we have basically 3 primary radiation mechanisms going on here. We have the jets that radiate in synchrotron, and that is why we see them in the radio. And we have the disk acts like a black body. And then we have what we call the corona, which is a cloud of plasma that sits around the central parts of the accretion disk on top and below. And what that does is the photons, the X-ray photons, so the accretion disk radiates in as a black body in what we call the soft X-rays. So these are the low energy X-rays. And these low energy X-ray photons get upscattered in that corona. There's highly relativistic electrons and particles and stuff swirling around there. And so the soft X-ray photons get upscattered in that corona to hard X-rays. And that is what we see. I'm going to show you some examples of spectra afterwards. But so these are the 3 main mechanisms, radiation mechanisms, that I want you to bear in mind as we go through the next couple of slides. So we have the jets radiate in the radio via synchrotron, and then we have X-rays coming from the accretion disk. And so, as I already mentioned, radio X-rays, so the way to fully study these sources is by trying to observe them in as many wavelengths as possible, and as you read out my thesis, the title of my thesis was in fact multi-wavelength observations of a couple of targets. And so for these microquasars, we primarily use X-rays, up to hard X-rays, gamma rays. People debate about where the actual boundary is there, and then of course the radio. And there are people who study them in the infrared, and the visible is primarily for trying to determine the nature of the companion star, but we're going to focus at the 2 ends of the electromagnetic spectrum. Radio, for which we can use these wonderful ground-based dishes, and then X-rays for which we need to lob detectors up into space. So what do we learn from X-rays? This is 1/2 of an X-ray spectrum, because I'm going to show you the other half in the next slide. And what we have here is on the x-axis, we have the energy. These X-rays we talk about, we refer to them in keV. So this is what we call the soft X-rays, about 1 to 10, 1 to 20 is the soft X-rays. And here we have the intensity. And here we're going to focus just on the red curve, and we call this the high soft state. And that is because we see a big bump here in the soft X-rays. And the way we interpret this is that this is a signature of black body emission. And so what we're looking at is, this is the scenario that we're seeing. We have the black hole and we see the accretion disk, and we are seeing pure black body emission from the accretion disk as it's swirling around the black hole. So that's basically what we're looking at. At the opposite end of the spectrum, really, we have the hard X-rays, and we're talking about anything from about 20 keV up to 1 GeV. And what we see here instead is a bump. We're looking at the blue curve here, and we see a bump that then descends as a power law here at the end. And what we infer from that signature is we are seeing the upscattered, Compton upscattered soft photons from the disk that are being upscattered through the corona, and they're creating, so that they're boosted from the lower energies, they're boosted to the higher energies, and that's what we're seeing as a signature here in the high energy end of the spectrum. And we put them together, so essentially we know that if we're doing a single observation and we're only seeing the black body signature, we know we're looking at the accretion disk, we're seeing the accretion disk, and we know we're looking at something hot. If instead we only see the signature of the Compton upscatter bump here, we know that we're seeing a corona, we're seeing something that's very energized and very energetic. But it's not that simple.
Excuse me.
Yes,
When you talk about them being boosted, are you talking about the photons themselves?
the photons.
So you're talking about a photon getting knocked by another electron to get boosted up?
In the corona.
Okay. I heard about the photon getting up boosted up.
In the corona here,
I
so.
do chemistry, so I do much lower energy.
That's a very good question, though. Right, so this is actually some of the thesis work that I did. I'm showing some of the stuff that's pretty ancient by now, but there's another source called GX339-4, and okay, there was a fantastic X-ray satellite that operated from the mid-90s or so, I think, until the mid-2000s, called the Rossi X-ray Timing Explorer. A fantastic mission. It had, I think, 3 or 4 instruments on board, of which one was the all-sky monitor. And it was, I think, one of the first times that scientists had put an all-sky monitor in X-rays. There were several missions prior, but I think, yeah, they did sort of all-sky surveys. But what the XTE team did was they made the data public immediately. And so they monitored the whole sky at the soft X-ray, so about 2 to 10 keV. And anybody could go into their data archive and pick out, any object and make a light curve. So a light curve is you have time on the x-axis and you have intensity on the y-axis. And so what you see is the behavior is not stable over time, but it has all these fluctuations and variability. And on the bottom panel there, we have BATSI, which is one of the 4 instruments on the Compton Gamma Ray Observatory, another fantastic mission. It was one of NASA's 4 great observatories. And it was deorbited in 2000 or 2002, but absolutely fantastic. They did the same thing with their all-sky monitor, or equivalent of all-sky monitor. The team just put the data out there for anybody to plot. And so this is the BATSI data down here, and that's the hard X-rays. About 20 to 100 keV was the energy range for BATSI. And so when I started my thesis work, I was looking for fun things to investigate. And so I was rooting around in the archives of the XTE team, of the BATSI team, and so on. And somebody had been talking about GX339-4, so I thought I'd go take a look. And I thought, okay, so I plot these light curves, and I plotted them, I saw there's all that variability, great, that's fun, but there was not much I could do without either X-ray spectra, which were proprietary, that data was proprietary. And so I thought, okay, well, we can see what we can do with this. We know that the soft X-rays are telling us there's the presence of an accretion disk, and we know that the hard X-rays tells us that there is some form of corona. And so that's the sort of geometries that we're looking at. But as you read out, I went back to Finland to explore my Finnish roots. And while I was there, this happened, that snow. And that snow came right up to okay, this was the first floor. This was not like the third floor or anything like that. It was the first floor, and some of it was drift. But that's the view from my office in January in Finland. Well, guess what? You also mentioned that I went down to Australia a lot. And note, this is January in Finland, okay? And this is the view that I had when I arrived in Australia, like 2 days later. Guess where I would prefer to be,
I was gonna say, that's probably why
I
your
love
ancestors
snow
left
too.
in the first place.
Yeah. Exactly. So I was pretty lucky, during my time in research. So I worked with Professor Richard Hunstead. You're going to see a photo of him in a minute. He was very much my mentor. He was at the University of Sydney. And the wonderful thing about it is, of course, they're the Southern Hemisphere, and in the Southern Hemisphere, their school year runs from March to December. And so Richard was always free January, February. So when I would tell him, oh, I think I need to catch up with you, do some research, he'd say, come on over. Well, I had absolutely no problem leaving Finland in January to go spend a month with Professor Richard Hunstead in Australia. I had a really good time, and in fact, I'm going to share some fun things with you. I loved being there so much, and so that's Richard. He passed away a few years ago, unfortunately, but my absolutely beloved mentor. And this is his porch, their back porch, and the rainbow lorikeets would just come and hang out with us, and there were a couple of cockatoos as well, and I absolutely love them. And then we also had the little possum. A little possum would come, and she'd just climb up the screen, and she loved apples. And she was so cute. So I'd spend time with little Possy. And Sydney Morning Herald, by the way, that's their main paper, and I absolutely, it was great. And then there are also things that like to hurt you. These are blue bottles. Do you know blue bottles? Portuguese man o' war? Yeah. Okay, so they call them blue bottles down there. So those are Portuguese man o' war. And then another thing that cropped up was, you might not see it here, but there's the tentacle of what's that octopus? Blue-ringed octopus.
Oh.
So that's, I think, one of the most venomous creatures on the planet. And Richard and his wife Penny and I, we were just hanging out in rock pools, and we were looking for all sorts of treasures in the rock pools and we had just put our hands in that rock pool to look for shells and so on, and then this tentacle just popped out. There it is, and we were like, oh. And then, of course, we know that Australia is full of spiders, and there's the sort of, that's just one, little creature that would just hang out, and yeah, it was fun. And but most importantly, Australia has a very long tradition in radio astronomy. They had some of the big pioneers in radio astronomy were based in Australia, and some of the early experiments were using repurposed wartime radars, and just using them, using the sea as, that's another story. Anyway, they're big pioneers in radio astronomy. And this is the Malonglo Observatory Synthesis Telescope, otherwise known as MOST. It's outside of Canberra. It's run by the University of Sydney. And it is just this very simple, it's nearly a kilometer long. I think it's about 800 meters long or so. Just a mesh array of dipoles and all that. And that is just out there outside of Sydney. And it's a synthesis telescope, and that means that you can't really point it, you just have to wait for the Earth to turn, or whatever target is above you, you get the data for. But thankfully, GX339-4 is right on top. And so we got a nice, Richard when I went down there, in fact, he said he had radio data of GX339-4, and so I reduced the data and got those flux density points. And so again, we have time on the x-axis and flux density on the y-axis, and lo and behold, that series of data, oh wait, first of all, we have to, okay, that's intensity. That's just single data points intensity. But there's another piece of the puzzle coming up. Oh, tenterhooks here, huh? And that is, I also had the good fortune of visiting the Australia Telescope Compact Array, which is a small array. It's 6 dishes of 27 meters each. If you know the VLA, I think that's 27 dishes of 25 meters. Compact array is 6 dishes of 27 meters. And of course, I've already mentioned Australian wildlife, so we have the kangaroos. This is a little photo of the little kangaroos hanging out. And we also found a brown snake coiled in one of the detector thingies, but I did not take a photo of that. And so I'd like you to pay attention to the radio dishes down there. This is not my video, but this is the sort of thing that one did see when one was observing in Australia. Such a lovely country. So, what we have up there, top left, is the intensity light curve of GX339-4. And where the green arrow points, the compact array did an observation and it showed an extended source. If this were a point source, so if this were just the X-ray binary that we're observing, it would just be a point source. But instead we're seeing some extension. And it happens at the time, just before the the light curve starts to rise. And when we look at it all together, we see the arrow points to when that extension started to appear, and we see that there's there's an outburst in the soft X-rays and an outburst in the hard X-rays as well. And so we realize that at that time we have an X-ray binary with we're seeing some of the disk, so there's some of the disk there, and there's the corona, but we're also seeing jets. So we're kind of now really noting the similarities with, no, let me backtrack. So now we're really starting to construct a more detailed picture. But it's not so simple, because this original, the two opposite states that I was talking about, the high soft and the low hard state, or the high state, the low state, suggests that either you have an accretion disk, or you have the accretion, or you have a corona obscuring the accretion disk, so you're not seeing the accretion. So in the blue curve, you're not seeing the accretion disk, and in the red curve, you're not seeing a corona. But in this case, we're seeing a bit of everything, because we have the soft X-rays, we have the hard X-rays, and we have the radio. And so,
Excuse me?
yes,
With the radio, what are the units for the y-axis?
millijanskis,
Okay, thank you.
yeah. The unit of flux density in radius Jansky.
Okay, thank you.
You're welcome. And so what we can do is we can really go very esoteric here and start to deconstruct the X-ray spectra that we get. So this is a full spectrum from a source known as Cygnus X3. And this is from the spectrometers on board the Rossi X-ray Timing Explorer. And so here we have the raw data, it's the blue and the red crosses up there. And what we can do is we can try and model the data and try and see what components fit the model best. And so here, this was another student of mine, Linnea Hjalmarsdottir, and she concluded, she did say that it's a little bit hand-wavy, and it all depends a little bit on what inputs you use at the very start. But, you know, this paper got published, and a lot of people did quite, agreed with a lot of the conclusions. But so what we're seeing is, in fact, we're not seeing just a disk, which is the green curve, and we're not seeing just the corona, which is the blue curve, but we're also seeing a combination of components in there, including do I have that here? Yes, including reflection from the disk itself. So all the different emission processes here so we're not going to worry about the radio right now, but we're just going to look at the X-ray scenario. So we have the direct black body emission from the disk, and that's in the green there. And then we have the disk photons that are upscattered through the corona, and that would be the blue curve there. But then we also have that reflection component, which is that there are photons from the corona that impinge on the disk, and then they get reflected off the disk. So we also have that happening. And so this is the soft photon going into the corona getting upset, and then we have direct, that's the non-thermal, no, that's the, it doesn't matter, it's a thorny thing up there, but anyway, so this is the full scenario. So we're not seeing, so that's where we're seeing a combination of having both the presence of a corona and the accretion disk that extends a little bit into the corona. And we have all of this, all of these processes going on here. And at the same time, that jet is doing something weird in there as well. And so we can conclude from looking at these spectra, all the different types of geology. These are the main states that we can deduce from the X-ray spectra, and they are color-coded. So when we have we can start with the ultra-soft state, which is the red curve there. And as you can see, the red curve, it peaks at the soft energies, so that's the peak of the black body emission, and there's absolutely no signature of any corona. So we come up with a little cartoon like the second one from the top. And then we can take another random one. Let's look at, for example, the hard state. So the hard state here, you see the disk is truncated, there is no disk. Or very little disk. It's mostly dominated by the corona, so it's mostly dominated by the Compton upscattering, and that's why we get no signature of the disk here, but we get a strong signature of the corona. And so we can play around with X-ray spectra like this and try and figure out, what's the disk doing, what's the corona doing, and so this is. So that's what we can learn from X-ray spectra, and from light curves we can also just simply with light curves we can also see similar scenarios or come up with similar scenarios. So again, the light curves, it just shows the variability over time. Here we're looking at days. On the left-hand side, we have the soft X-rays in the middle panel, radio in the bottom, hard X-rays in the top. We see a lot of variability. But the fun thing, remember what I said about timescales, is if we take, I can't remember exactly from where this is, but I think it's from somewhere in here, we can take a segment of the light curve and we see that this is only 40 minutes long. This is like less than an hour here on the x-axis. And look at all this stuff that's going on here in the span of about half an hour. The black line here are the soft X-rays, and then the blue is the radio, and the infrared is a totally other story. I'll have to have another whole talk about that. But so here we see the soft X-rays. There's something going on here. They're very active, and then suddenly they disappear. And after they disappear, shortly after they disappear, the radio comes out. And so what we think is happening there is this is just another representation. What we think is happening there is first you have jet activity, the disk empties out. So there's a jet ejection, disk empties out, the disk starts to refill, and there, top middle, the disk has refilled, then there's something goes unstable, it might be mechanical instability, magnetic instability or something, makes the disk unstable, and then that is probably what triggers an ejection event. And so we can kind of see that simply in this little light curve here that just shows, the soft X-rays disappear, that means there's no disk anymore. Where did the disk go? Oh, radio came up. The disk went into the radio jets. And this was another fun part of that study. I took the radio data, the soft X-ray, the hard X-ray data, and I tried to see if there were correlations between them. And we found some pretty strong correlations between the radio and the soft X-ray and the radio and the hard X-ray. And that meant that they were all linked, that you could not just think about the accretion disk independently of the corona and independently of the jet. And so this was the first time that anybody had done a study like this. And what that did was it spawned a whole interest in other people started looking at other microquasars. Here we have, so that we looked at was JX339-4, and here we have a list of some others, XTJ1118, B404 SIG, and so on. And when we plot the radio luminosity against the X-ray luminosity, you can see that there's a pretty tight correlation. But guess what? It gets even more exciting, because what we can do is we can extend that line. Down at the bottom left we have microquasars, but guess what? Over here at the top right we have all the quasars in AGN.
Wow.
People started doing these same studies of correlating radio and X-rays, and they are tightly correlated all the way up to, from stellar mass black holes all the way up to supermassive black holes. And so this is other people who have been doing that, who are doing that study, but that just shows that that whatever happens in microquasars is we can sort of transpose, what's happening in microquasars to quasars. So, okay, all of that's a lot of fun. I think we all have a lot of fun playing with data and trying to figure out what it does, but ultimately, we ask the question like, why study microquasars? And I think one of the fundamental things is that accretion is an incredibly efficient way of extracting energy in the universe. The efficiency of the sun's fusion process is only about 0.7%, but accretion is up to 10%. And so people want to understand, physicists, theorists, they want to understand exactly, what are the mechanisms of accretion, how does it behave, and so on. And mainly, black holes are a fantastic test for relativity, of course. And probably one of the bigger reasons is that jets are ubiquitous. There are jets in practically every single object in the universe. I mean, from protostars to pulsars to gamma ray bursts, of course, protoplanetary systems, and so jets are everywhere. So if we can understand jets in one system, we can probably understand them, or at least try to understand them in other systems. And by the way, up here, that's SS433, that's the supernova remnant that we talked about at the very beginning, where the X-ray source is sitting inside. But we actually still don't know how jets are formed. I mean, we have some vague ideas, but we still don't know how they're formed. We don't know what affects jet power. Could it be black hole spin? Could it be black hole mass? Could it be the mass accretion rate, fluctuations in the mass accretion rate? Could it have something to do with magnetism? Could it have something to do with recombination? We still don't know, and that's what makes it all very exciting. But we have a formula. With microquasars, we have a formula. We have a compact object, a companion star, and that gives us both accretion and ejection. And through that, we know that black holes only interact through gravity, so we can't really see them. But by looking at all these other things, we can start to probe the physics in gravitational fields that are inaccessible here on Earth. And in other words, I mean, we really are looking at extreme physics. And so I think microquasars are perfect little laboratories for that sort of exploration. And so back to the question, how can we see black holes? Well, when they accrete matter. And I think when they accrete matter, that is the best and closest way that we can get to really probing the true nature of black holes. And, but I just want to conclude, I have just a few slides left. The fun thing about them is that you can observe them. Of course, you're not going to see the jets or anything, but in the September 2019 issue of Sky and Telescope, Dave Toastison wrote a Going Deep column on microquasars, and there's Cygnus X1, the very first X-ray binary to be identified in 1973, and that was shown to have jets. And here's just a list of some that you might want to point your telescope at. LS 5039, SCO-X1. SCO-X1 is actually a neutron star. V4641 SAG, SS433, which is the one that we talked about before. It's magnitude 14. And P13, I have no idea what that is, and I edited that. I have to go back to that. So when you are looking at these objects, you look at Cygnus X1, and all you see is a dot in your telescope. But when you look at that dot, just think that that's actually what you're looking at. You're looking at this system, that has a black hole, it's accreting matter from its companion star, and is shooting jets of plasma at nearly the speed of light. And I think, it's worth taking a peek at. But I have one last question. Anybody here a Rush fan? Good. Guess what? In 1977, Rush wrote a song called Cygnus X1, okay? And it's all about, you can't see it telescopically and so on and so forth. And so 77, that was, when did I say Cygnus X1 was discovered? 1973. When were quasar jets discovered? 75, right? Does anybody remember when the microquasar, the SS433 jets I mentioned?
79.
79. When did they write the song? 77. And look what we have here. We have a jet. They knew about Cygnus X1's jet. So kudos to them. So with that, yes.
There was a question online from Dennis Beaches. He's asked, does Cygnus X1 emit sufficient amount of radio waves to be imaged by the Event Horizon Telescope?
Oh, very good question. I think not, but I would have to investigate that. I don't think it's a very strong radio emitter. I think that the jets that so it has jets, that's a very good question. I have a feeling not, but I would like to maybe investigate and get back. So who was that?
Dennis Beaches.
Okay. I will try and get back to you. Okay, sorry about that. And with that, I just want to say thank you.
You don't get to ask questions.
Yes, sorry, questions?
Diane, I have a question.
Yes.
So these things are rare.
Microquasars? Yes.
Is it because the systems are rare? Or does it also include the fact that the very mechanism that turns them on, there's only a limited supply of energy, right, of matter to fall into the accretion disk? What's the lifetime of a microquasar? Are we just fortunate enough to see these in their prime?
That's a really good question. That was something that I wished I had covered, and so I'm so glad you asked that. They are rare probably because, okay, so they do repeat. So most microquasars, or most of the ones we know, have repeat ejection events, so we do see them over and over again. Some we've seen only once, but I think there are more out there. It's a very fleeting time. As you saw the 1915 event, in 1 month already the radio jets were starting to fade. So I think we're just not catching them, and we just don't have enough telescope time. There are no radio telescopes that can do all-sky surveys like the X-ray all-sky monitors. And so we might just not be catching them because all X-ray binaries, by definition, have accretion disks, because otherwise we wouldn't be able to see them, because we call them X-ray binaries because we're seeing the accretion disk that is radiating in X-rays. And I think it depends on the nature of the X-ray binary, like what the companion star is, how big the accretion disk is, how stable the accretion disk is. But I think eventually most accretion disks do go unstable and will have to, but that's part of the question, what do you need to, what mechanisms do you need to eject jets at velocities so that we see the synchrotron radiation that we can, catch with our radio telescopes. So I think it's a question just of not catching them. And then some might just be very faint, because they just might not have the power to produce the sort of intensities for us to catch with our radio telescopes. So, good question, thank you. Yes?
You mentioned with the X-ray satellite being launched, that some of the data were proprietary?
Yes. The way it works with missions, the proprietary at least for 1 year, the way it works with these missions is there are usually instrument teams who get first dibs on data, and they get to play around with the data for a year, after the year it goes public. But then there are also scientists from all other, institutes from around the world can apply for observing time. And if they get the observing time, they get the data and they get to play around with the data for a year. And then after that, it's released to the public in general. Some missions operate a little bit differently, but in general, that's how it works. But that would be like the spectral data.
You asked to look at this object, you get first dibs on.
You get first dibs on, exactly.
I didn't know if it was something like military or something like that.
No, just that. And, but whereas some of these teams, if they have the all-sky monitors, they let the whole world see the activities,
all the time.
from all the time. So that people can go and do follow-up observations at other wavelengths and just make it more useful to the whole community. So, yeah,
Thanks.
yes.
Two questions. Why do black holes form or end up in the center of galaxies? And also, I successfully pulled knowledge of physics out of my two remaining brain cells. Scattering is reverse Compton scattering when you have atoms with electrons that are kind of permanently in excited states, and then a photon comes along and gets energy from the electron?
It is yes, you've got the photon that is, so you've got a relativistic plasma, which is the corona is like the relativistic, so you have very fast moving particles within that corona. And as a photon goes near one of these particles, it gets the energy from all that movement and gets boosted up. Because the regular Compton scattering is instead when you have the energy of a photon decreases as it goes around, yeah.
Okay, and black holes?
Yeah, which came first? The
I was
galaxy or
wondering,
the black hole?
why do they formed in the middle of galaxies, or why do they end up there?
I think that's what the James Webb scientists are trying to understand right now as we speak. I don't think, we still don't know what formed first, whether, I think they're still debating that, whether black holes formed in the early universe and then slowly galaxy stuff accreted around them, or whether galaxies formed and then supermassive black holes were generated at their centers. I don't think I think they're still debating that, I believe. Yeah, so it's a very good question. Yes, Kelly?
So you said that we still don't understand how jets form, but there's this strong correlation. If you've got accretion, you're likely to have a jet.
Yes.
What I have heard said is end wavy. It's accretion that kind of overshoots and gets shot out the poles.
Yes.
Is that?
Yes. That is one, definitely that's, I think, what I was alluding to with the light curve there. But the question then might be, how can they be so collimated? Because they're quite collimated, at least at the bases. And that's where a lot of people invoke magnetism, magnetic fields, recombination of magnetic fields, because a lot of these disks are also magnetized. And so they think that maybe so the disk builds up, the matter builds up, and then suddenly there's a sort of recombination of the magnetic field line, and that's when everything whooshes out. And so that's one scenario.
Is there any polarization that they get in the radio?
Yes, for sure. Yes, definitely, and there are, there's lots of studies being done on that, yeah. Circular polarization, linear polarization in the jets, and yeah, for sure. So I really want to thank you all for your attention, but I have one last question. I just would like to know, is there anybody here, and this is where I hope not to see a show of hands, is there anybody here who's not a subscriber to Sky and Telescope? Because if you're not,
Past and future.
I have a little card here that has a cute little QR code on the back that will give you all the information on Sky and Telescope and a free digital download. How can you resist?
I'm a wax subscriber.
There you go. Thank you so much. All righty, one more. Anybody, oh, excellent, oh, lovely. Here you go.
My last question is where can they work like yours?
Oh, SPAHA, S-P-A-H-A. Do we need some on this side?
Are you an amateur telescope makers of Boston member?
I am. Here you go. And if you are a subscriber, you can give one to your friends. Thank you.
I didn't realize
Excellent.
I didn't realize the editor-in-chief also was in the sales department.
Yeah, we're a small staff. We gotta double up. Thank you so much.
Thank you.
Thank you, Dr. Bennett. Surely, Rich and Glenn must consider adding the microquasar of the month.
We do that next month. ATMoB will be in the sky.
Yes, exactly.
Thanks everybody for coming tonight. And the July meeting was approved, so we will see you on July 10th at 8 o'clock.
Thank you, Carrie.
Good night, everyone.